Alright guys, let's take a look at number one. We're given the mass of a dragster, we're given the final velocity, and we're given the time. It says it starts from rest, so that's a VI of 0. The first thing we got to do is find the acceleration. So we can use our definition of acceleration to solve for A because we have everything else. Next we got to find the force. Well, we know that F is equal to ma, and we have the mass and the acceleration, which we just found. I'm going to use a version of the acceleration that has a few more decimal places to make it a little bit more accurate, and then we can find our force. If we want to find the force that the seat exerts on the driver, then we're going to use the same thing, except instead of the mass of the car, we're just going to use the mass of the driver. So instead of 873 kilograms, which was the entire race car, we're just going to use 68, which is just the mass of the driver. Number 2, we are given the mass of a car. We know that we're going along at 10 meters per second, then we accelerate up to 30 meters per second over a time of 10 seconds. Before we can find the force, we got to find the acceleration, because for every force there must be an acceleration. So we can plug into our definition of acceleration and figure it out. It's 2 meters per second squared. Now we know that F is equal to ma, so we can just plug in our mass and our acceleration to find the force. Here we are, number 3, we're jumping off of a tower. We're given the height of the tower. We can assume that we're starting from rest, if we're just sort of jumping off. And we got to find the velocity right before we hit the water. We know that the acceleration is going to be negative 9.8, because gravity is what's pulling you down when you jump off of something. So this equation works well to find the final velocity. Don't forget to square the VI and then take the square root at the end. So we have everything that we need. We can just plug in. Notice how I'm using negative 10 down there. When I solve for VF, I use negative 10. I should have put a negative in the bank. Actually, I can add it right now. Here we go. Let's add a negative there, because we're going downwards. Okay, so now that we have the final velocity, we need to find the force exerted by the water. Well, in order to find the force exerted by the water, we need to find the acceleration exerted by the water. So let's write down everything that we know. When we hit the water, we're going negative 14 meters per second. We know that because that was the answer to part 1. So we're hitting the water at 14 meters per second. We're going to come to a stop eventually, right? Because you jump into water and then you slow down real quick and you come to a stop. So my VF is 0. It takes me 2 meters to come to a stop. It's really negative 2 because you're moving downwards. So we want to find that acceleration between when you hit the water moving at negative 14 to when you stop over a distance of 2 meters. What is that acceleration? Because once we know that acceleration, then we can know that force. So considering everything that I know, this equation right here will be the best to find the acceleration. So let's rearrange it to solve for A. And now once I have my acceleration, I can just plug that into F equals ma to find the force of the water. So this is a pretty big acceleration, right? I mean, this is like about 10 times, I mean, not 10 times, about 5 times the acceleration of gravity. So water slows you down real quick. We have the weight of a motorcycle. I want to remind you that the weight is the force of gravity. If your motorcycle weighs 2,450 newtons, that means the force of gravity is 2,450 newtons. That's the definition of weight, is the force of gravity. So if we know the force of gravity, and we know the acceleration, it's always negative 9.8 when you're on Earth, then we can find the mass just using F equals ma. I'm going to rearrange the equation here for m. You don't have to do that if you don't want to. You can just do a quick little division, and we get the mass of the motorcycle. So now we have a helicopter that's accelerating upwards. So automatically you got to stop and think, all right, I need to draw a free body diagram. Why? Because you have more than one force. We know that there's the force of gravity. There's always the force of gravity. So if you're accelerating upwards, that means you must have two forces. The force of gravity pulling down and the force of the propellers pulling you upwards. So anytime we have more than one force, we need to draw a free body diagram. So we have the force of gravity pulling down. I'm going to call it the force of lift pulling up. We can set up Newton's second law. The sum of the forces equals mass times acceleration. The sum of the forces is going to be the force of lift minus the force of gravity. The way I know that is because you want to always take the positive force and then subtract the negative force in the opposite direction and set that equal to ma. So what I want is the force of lift, so let's rearrange the equation to solve for the variable force of lift. And I have everything else. I know the force of gravity, it's just mass times 9.8, so 4,500 kilograms times 9.8 is the force of gravity, plus now the mass of the helicopter, which is 4,500, times the acceleration of the helicopter, which is given in the problem. So now I just plug this into my calculator, and I can find the force of lift. So clearly it takes a lot of newtons to lift a helicopter off the ground. Here we have another kinematics type of problem. We're going at 14 meters per second, and then we're going to slow down to rest. We're given the distance that takes place. If we want to find the force of friction, you have to find the acceleration. You cannot calculate a force unless you have acceleration. So let's find the acceleration first. This kinematics equation is going to work best for us. We can rearrange it and solve for a, then plug in everything that we have. Don't forget to square that 14 up there. You plug it into your calculator, you can get the acceleration. It's negative because we're slowing down. And then just plug that into F equals ma, because the mass is given and we now know the acceleration. So the force is going to be a negative number, but that's okay, because we're slowing down. It's just like acceleration. If it's a force that's speeding you up, it's going to be positive, and if it's a force that's slowing you down, it's going to be negative. Number 7 is a great problem, and you got to remember what a scale is. A scale is just a thing that reads you the normal force. So when you're standing on a scale, the force of gravity is pulling you down, and the normal force is pulling you back up. If there was no normal force, then you would fall through the earth and you would end up in China. Force of gravity pulls you down, normal force pulls you up. So all a scale does is it tells you how much it's pushing you up. And so it's essentially telling you what the normal force is, which is equal to the force of gravity because you're not moving. Okay, so let's consider an elevator that's moving up. Your force of gravity is always going to be the same because your mass and your acceleration never changes. I mean, the 9.8 never changes. Now let's consider an elevator going down. Your force of gravity is still the same, but this time your normal force is going to be a little bit less. So let's take a look at this. In the one in the middle, your normal force and your force of gravity are identical. You're just standing in your bathroom. You're not accelerating. Everything's balanced. They are equal. Consider the diagram on the left. An elevator moving up, your normal force is going to be bigger than your force of gravity. You feel heavier while the elevator is moving up. So your normal force is larger, you have unbalanced forces. As I mentioned earlier, the one in the middle is balanced. And then the one on the right is also unbalanced. An elevator going down because your normal force is going to be less. You feel a little bit weightless. This is why when you're going down, either in an elevator or in a roller coaster, or you jump off the top step in your house, you feel weightless because your normal force is less than the force of gravity. So one more time, elevator going up, you feel heavier because the normal force is larger. When you're going down, the normal force is less, so you feel weightless. And then when you're just standing in your bathroom, your forces are balanced, so they are identical. Now, let's solve this problem here. It says that as we're going up, the scale reads 936. Well, first of all, we need to find the mass before we do anything. We got to find the mass of Mr. Warner. We know the force of gravity, it's given 836. We know the acceleration of gravity, 9.8. So we can plug into F equals ma to find the mass of Mr. Warner, because we're going to need that later on. So once again, we're just using the force of gravity, which is given. We're given the acceleration, which we already know, 9.8, to find the mass of Mr. Warner. Now, let's draw a quick FBD here. We got the force of gravity going down. We already know what that is. It's given, 836. And the force of the scale is given in the problem, 936. Remember, a scale tells you the normal force. So if the scale reads 936, that means the normal force is 936. And we already know what the force of gravity is. So we can set up Newton's second law here. Sum of the forces equals mass times acceleration. So it's going to be 936 minus 836 equals mass, which we know, times acceleration, which we don't know. So all we need to do is divide to find the acceleration. And it's positive because we're accelerating upwards. We're going to solve the second part the same exact way. We can set up another free body diagram, the force of gravity going down, the normal force going up. This time we're given the normal force, 782. The force of gravity is still the same, 836. So we can set up Newton's second law again. Subtract the opposing forces, set that equal to mass times acceleration. It's still the same mass because it's still Mr. Warner. We can solve for acceleration. So we get a negative number, but that's okay because the elevator is going down. So if it's accelerating downwards in the negative direction, then the acceleration is going to be negative. Part C, what would take longer, starting or stopping? Well, stopping would take longer because it's a smaller acceleration. So if you have a smaller acceleration, it's going to take you longer to reach a certain speed, even if that speed is 0. Number 8, we have a weather balloon. I'm just going to draw a free body diagram right off the bat because I have two different forces. I have the force applied going up, that's what that little FA is, and I have the force of gravity going down. How do I know that? Well, it says in the problem, the balloon is released and exerts an upward force of 98. So there must be some sort of applied force pulling upwards at 98, that's the force of the balloon. And it's really easy to forget about the force of gravity, but the force of gravity is still there, it's always there. It's pulling the thing back down. I can calculate the force of gravity by taking the mass, 5, times the acceleration of gravity, 9.8. So now I have both my forces. The one on top is bigger, but that makes sense because the thing is going to be going up. So of course the one on top is bigger. Let's set up Newton's second law. The sum of the forces equals mass times acceleration. So 98 minus 49 equals mass times whatever acceleration. So I can solve for A. I can find that acceleration. So it happens to be 9.8, which is kind of confusing. It's just a coincidence. It has nothing to do with gravity. It just happens to be 9.8. Now for part B. We need to set up a little kinematics session here. We have the time given, we have the acceleration, which we just found. It happens to be 9.8. The initial velocity is 0 because it's starting from rest, and we want to know the final velocity. So we can plug into our VF equation to very simply find the final velocity. After the balloon is released, the only force acting on it is gravity. There's nothing pulling it up, there's nothing pulling it sideways. The only thing pulling it down is gravity. Now, we want to find when the velocity first becomes downward.
Mr. Stevens, can you go meet Miss Godetti in your room, please?
So let's think about this. When is the thing first going to be going down? Well, let me draw you a quick diagram here. You're going up and up and up and up and up and up and up, and then eventually you stop, and your velocity is 0 at that very tippy top. And then you start to go back down again. So when it's released, we know the VI down here when you first release it. You found that earlier in the problem. It's 98 meters per second. So we can use that as our VI, and then use VF up here equals 0 to solve for the time. Because we know the acceleration. The acceleration is just going to be negative 9.8, always pulling it down. Gravity is always pulling it downward. So using our VI of 98, using our VF of 0, using our acceleration of negative 9.8, we can find time. Looks like I forgot the negative in front of the 9.8. Let me add that right now. It should be negative 9.8 meters per second squared. Let me erase all this stuff. And let's keep going. So we can set up our VF formula, plug in all of our factors, and solve. We can rearrange it and solve for time. And after 10 seconds, it'll start to go down. Number 9 is Newton's third law. We have two people pulling on a rope, I guess, on ice. So we have two different forces because we're pulling on the rope here. But they're really the same force. Remember, Newton's third law says equal and opposite forces. Let's plug in some masses here. I think I put the boy on the left. He weighs 65 kilograms. The girl weighs 45 kilograms. And we know her acceleration. We don't know his acceleration. So how can we do this? Well, think about it. The forces are going to be exactly the same because Newton's third law says equal and opposite forces. Well, F equals ma, so ma must equal ma, right? So now we can plug in our numbers. We can plug 65 in our variable on the left, and we can plug 45 and 3 on the right because those are both given. So now we have an equation that's very easy to solve. We can just solve for a. We get 2.1 meters per second squared. So that is the acceleration of the boy toward the girl. And if you wanted to find the force, you could do that too. You could just do mass times acceleration for either one of them, and it would give you the same thing. Number 10, we have a baseball, initially at 30 meters per second, slowing down to 0 in a time of 0.005 seconds. We know the mass of the ball. First, we got to find the acceleration, so we got to bust out our kinematics skills. We can use the VF equation right here just to rearrange it and solve for A. That's a big acceleration, but I mean it's a baseball, and baseballs move pretty quick and they stop pretty quick too. Now to find the force, we can just do Newton's second law, mass times acceleration. So it's negative, is that okay? Yeah, that's okay, because the baseball is coming to a stop. So that's okay that it's a negative force because it's slowing it down. Newton's third law says equal and opposite forces. So if the force on the ball is negative 870, then the force on the person is going to be positive 870, because equal and opposite forces. Check out number 11. Two masses on a string. That's a pulley that I drew up there, and we have our two masses hanging down. Let's get some FBDs going on. We got multiple forces, so you have to draw a free body diagram. So I'm going to draw a free body diagram for each of these boxes. Now take a look at them. The one on the left, we have the force of gravity pulling down, the force of tension pulling up. The one on the right, we have the force of gravity pulling down, the force of tension pulling up. Same thing. Remember, the force of tension is the same throughout the entire string. So both of those FTs are identical. We got to do Newton's second law one at a time. You can only do Newton's second law for one particular system. So let's start with the one on the left. I circled it in pink. Let's do Newton's second law for that one. Sum of the forces equals ma. So that means force of tension minus force of gravity equals mass times acceleration. I need to start using some subscripts here because I don't want to get confused. We have two FGs here and we have two M's. So I'm going to use the subscript 1 for the system on the left, and I'm going to use the subscript 2 for the box on the right. So I have Newton's second law written out for the left side. Let's write it out for the right side in blue. Now wait a minute, why did I do that? Check it out. Here I did Ft minus Fg equals ma. And here I did Fg minus Ft. I did it backwards. That's because it really helps to just to know the direction of your movement. Think about it. The box 1 here is going to go up like that. So the Ft is going to be the force pulling it up, and G is going to be the one holding it back. But box 4, we all know that's going to fall. It's a heavier box. So box 4 is going to go straight down to the ground like that. So the force pulling it, the prevailing force is going to be the force of gravity, and the lesser force is going to be the force of tension. So it really helps for problems like this where you can just kind of see what's going to happen. It really helps to just make it the direction that you're moving. You know what I mean? So like the one on the left, it's going to move up, so make up positive. That's why I did Ft first. But the box on the right, the 4 kilogram one, it's going to move down. So I'm just going to make down positive. So that's why I'm going to do Fg minus Ft, because I already know it's going to move in that direction. And it just saves us a lot of stress to get that out of the way really early on. So let me rearrange both of these equations, the pink one and the blue one, for just Ft. Now, Ft is the same for both of these because it's the same exact rope, and the tension in any rope is going to be the same throughout that entire rope. So now I have two different definitions for the force of tension, but it's the same tension. So I can just set these two equal to one another. Let's do that. Now I have a bunch of different numbers here. I have the force of gravity, that's just mass times acceleration. I have the mass, I don't know the acceleration. I have the force of gravity for the other one, it's just 4 times 9.8. And I have the mass of the other one, 4. So now I only have one variable, a, and I can solve for that. So one more time, looking at how I solved that. The force of gravity, I know, that's just the mass times acceleration. The mass is given, I don't know a. I know the other force of gravity because that's just mass times 9.8. I know the m, I don't know the a. So I only have one variable, a, and we can solve for that. And that's it. Okay, I hope that this was helpful.